What is the sound of space? The idea that it's a vacuum, and therefore completely silent, is somewhat a misconception. And though sound as we experience it cannot travel through space, there are several intuitive ways through which we can extract the songs of the universe. Sound is present on each of the 8 planets and around the Sun. Meanwhile, it also emanates from the most extreme objects in the universe, neutron stars and black holes. And so this time out, we will be embarking on a journey of sound in space. One which will take us from the summit of Earth's atmosphere to the most remote corners of the cosmos. So listen closely as we experience the many haunting, eerie sounds of the universe. In the human context, sound is a sensation experienced by the brain, as it interprets sensory signals arriving in our ears. In the broader context of physics, however, these signals are the transmissions of vibrations between atoms. When a piano key is pressed, the string vibrates to impact the molecules of air surrounding it, transferring an energetic disturbance between atoms and thus kicking off an omnidirectional ripple of reverberations. These ripples eventually ring through the atoms of air in our ears, where the interior bones pick them up and pass them on to the brain. Evidently, this was a potent adaptation for avoiding predators, which emerged early in the evolution of complex life on Earth. In any case, what we experience as sound is simply the result of disturbances propagating through a dense medium of atoms, like the gaseous atmospheric layer surrounding Earth. On a temperate, dry day, sound waves course across the face of our planet at around 343 meters per second, or 767 miles an hour. But unlike the speed of light, for example, this is not a static, constant speed which applies everywhere. Quite the opposite, in fact. The speed of sound varies greatly according to the thickness, temperature, and composition of the atoms it is traversing. For example, hot air on Earth raises the speed of sound to about 355 meters per second, while freezing air slows it to 330 meters per second. Further up in the atmosphere, where air is much colder and thinner, sound seizes up to just 295 meters per second, or 660 miles an hour, becoming severely impaired and diminished in the process. And then, more than 100 kilometers away from the planet's surface, the density of atoms falls too low for audible sound waves to travel at all. Without a consistent atomic chain to traverse, sound cannot propagate effectively, and in the near vacuum of empty space, there usually aren't enough atoms to facilitate this. Hence the age-old, infamous line from the movie Alien that in space, no one can hear you scream. But even if sound waves can't travel in this environment, outer space is still brimming with electromagnetic waves, which unlike sound, do not require a medium such as atoms to travel. They have their own medium, the photon particle, including photons of radio energy which can be interpreted as sound to reflect the movements of plasma, giving us our first sound of space, Earthsong. Far from a true vacuum, the space surrounding Earth is perpetually permeated by a storm of ionized particles and radiation, most of which are captured from the Sun. These charged particles are governed by the electromagnetic force, and so become caught up and tethered by the influences in Earth's magnetosphere, a coma-shaped bubble and tail of influence created by our planet's magnetic field. As the Earth rotates, Changing electromagnetic influences stream through mounds of ions and subatomic particles and accelerate them, creating ripples of disturbance in their surrounding plasma, which manifest as waveforms which closely resemble sound waves. And because this plasma emits most prominently in radio frequencies, we can listen for these sound-like plasma waves to distinguish their various types, according to their distance from the Earth. In particular, NASA's two Van Allen belt probes, which studied their namesake toroidal bands of radiation around Earth in the 2010s, used radio-seeking instruments to sense changes in the plasma environment, indicative of accelerating charged particles sweeping over the detectors. Scientists were then able to shift this radio data into audible frequency ranges between 20 Hz and 20 kHz, yielding a handful of recordings of Whistler mode waves, the sound of Earthsong swirling far above the planet in space. Whistler mode waves come in various forms throughout the magnetosphere. They can be caused by lightning strikes on Earth, which leak electrical discharge beyond the atmospheric layer. These charged particles then ping-pong between the lines of the planet's magnetic field as they rise up into space. As they travel, the dispersion of their signals causes lower frequency emissions to lag slightly behind their high frequency counterparts, resulting in a falling, high to low scale, more reminiscent of lasers in a sci-fi movie than whistles. Lightning strikes have also been touted as a possible cause of so-called hiss waves, another type of Whistler mode wave, occurring much closer to the Earth in the dense, tightly bound bubble of cold ionized gas known as the plasmasphere. Also known as plasmaspheric waves, they resemble radiostatic more than whistling and make a deep-pitched hissing sound in audible frequencies. Finally, beyond the boundary of the plasmasphere, where ionized matter is sparser but also warmer, we hear so-called dawn chorus waves, named as such because they mimic birdsong, with a rising, low to high chirping sound, as electrons accelerate to relativistic velocities. Beyond our planet's sphere of influence, we can no longer rely on electromagnetic waves to pluck the strings of musical space. But this process of extracting whistling chorus waves can be applied to each of the other bodies in the solar system, including its main body, the Sun. When it comes to our neighbourhood star, it is merciful that sound doesn't travel in space, as the true, unmuted roar of its nuclear furnace would obliterate the eardrums of humanity. Alas, the interplanetary medium only contains a scattering of atoms per cubic metre of space, not substantial enough to carry the Sun's immense vibrations. But closer to the bounds of its photosphere, plasma waves are drummed up within its corona as the Sun moves through space, wobbling as it goes. And over the decades, we've launched a handful of pioneering missions to study the flows and movements of particles within this coronal atmosphere. As a result, Scientists at the Stanford Experimental Physics Lab were able to process more than 20 years' worth of solar heliospheric observatory data to derive the sound of the vibrating sun. More recently, the revolutionary Parker probe has made several of humanity's closest ever solar approaches, gracing the superheated atmosphere and mapping a host of plasma waves in exquisite new detail, which, when shifted into audible frequencies, provide us some of the eeriest Whistler mode recordings yet. We can also extract these waves from other atmospheric worlds in the solar system. In fact, the Parker probe itself made measurements of changing electromagnetic fields in the ionosphere of Venus when it flew by the planet en route to the Sun in 2020, revealing the unnerving sounds of Venus's electric wind. As we mentioned, the speed of sound is not static, and each atomic gas has its own arbitrary speed at which disturbances ripple through it, according to the composition, temperature, and rigidity of the medium. The scalding, suffocating atmosphere of Venus, almost 100 times the pressure of Earth's, catalyses the speed of sound to upwards of 400 meters per second, at least 20% faster than on Earth. And by arriving faster, sound at this speed would be louder and clearer in theory,
and higher in frequency and pitch.
In practice, however, its quality would be hampered by Venus's CO2-rich atmosphere, which absorbs higher frequencies,
resulting in a muffled, booming, and lower-pitched audio.
Hence, it would be tough to hold a coherent conversation on Venus, even if our bodies could somehow survive its hostile conditions. The same is true for our other terrestrial neighbour, Mars, albeit for a different set of reasons. Unlike Venus, the Martian atmosphere is 100 times thinner than Earth's, and sound only carries about 240 meters per second, almost twice as slow as on Venus. In such an environment, noises would be considerably quieter, and like on Venus,
Their range would be blunted by the absorption of high frequencies, making it similarly difficult to converse in Mars's CO2-dominated atmosphere.
That being said, in 2021, NASA's Perseverance rover was able to return a real-life recording of the gentle Martian breeze over the whirring of the probe's instruments, far removed from the chaotic turbulence of the Venusian atmosphere. The slowest speed of sound in the solar system is not found on a planet, but rather on the gaseous frozen moon of Titan, where it carries at less than 200 meters per second. For the planets hosting it, however, it's a different story. The two gas giants of the solar system are both many times larger and heavier than their terrestrial neighbours, with much thicker atmospheres extending tens of thousands of miles from their cores. These atmospheres are made of warm, liquefied hydrogen and helium gas, which unlike CO2, facilitates higher frequencies, resulting in a higher pitch. Sound would be louder and clearer on both worlds too, rattling between light elements in their upper atmospheres at more than 1,000 meters per second on Saturn, and perhaps as fast as 1,500 meters per second on Jupiter, practically the same speed as in water here on Earth. But these speeds would skyrocket the deeper into each planet you travelled, and over any vast distance, considerable pressure gradients influencing the speed of sound would severely hamper its quality. The ice giant worlds, on the other hand, have higher shares of volatile substances in their atmospheres, rendering them cold environments
where sound is muffled and lower pitched,
carrying around the same speeds we experience here on Earth, 300 meters per second on Uranus and around 350 meters per second on Neptune. We've never sent a mic'd up spacecraft to either of these worlds. In fact, only one mission has ever visited the ice giants up close, Voyager 2, which transited the magnetospheres of all 4 large planets in a single swoop during the 1980s. It too was equipped with radio receivers and plasma probes, allowing the craft to feel its way into the boundaries of each world's magnetic influence. And in doing so, Voyager 2 returned radio recordings of plasma for its approaches and flybys of all 4 large planets, offering unparalleled new insights into various aspects associated with each. In 2012, Voyager 2's twin spacecraft, Voyager 1, was confirmed to have become the first probe to exit the Sun's heliosphere of emissions, thereby reaching interstellar space. On 2 occasions in late 2012 and mid-2013, the spacecraft flew through its first mounds of interstellar plasma, and while the majority of its decades-old instruments had been terminated by this point, the craft's capacity to sense radio photons persisted. These flashes of radio energy were heard as banshee-like screams of helpless particles suspended in the void of interstellar no man's land. These are the most remote sources of sound we've ever recorded in space. Beyond them, we stray into unexplored, uncharted territory. But radio astronomy still provides us the perfect platform for extracting sound from space, including from much further out amongst the stars. In the late 1960s, as radio interferometry was in its fledgling stages, a different kind of sound began cropping up in the sky: pulsars. Pulsars are radio signals from rotating neutron stars, which swing parallel funnels of emission around their circumferences, periodically pointing in the direction of Earth. These signals are then detectable to us as a stream of precise, regularly timed pulses of photon energy, which, like many of the aforementioned signals, are better represented and appreciated in audible frequencies. The first pulsar to be discovered in 1967 has a period of about 1.3 seconds, and its groundbreaking nature set humanity on a quest to uncover dozens more of these strange signals. Soon after, the Vela pulsar was uncovered, spinning 11 times per second to yield a much more ominous knocking sound, which has achieved particular attention and notoriety online. Another of the first handful of known pulsars resides in the Crab Nebula, belonging to a relatively young neutron star of only 1,000 years, which spins some 30 times a second, yielding a higher frequency signal. The fastest spinning pulsars, with the most regular signals, are millisecond pulsars, which spin more than 100 times every single second, rendering shrill-like beeps of incredibly high frequency. And the most powerful type of neutron star, the magnetar, is responsible for a variety of exotic, obscure sources of emission, like fast radio bursts, which stream from their quaking crusts. By themselves, neutron stars emit a myriad of different radio sounds. But when two of these dead stars come together, they emit a sound of a much different nature, gravitational waves, the likes of which can be heard across the entire universe. Gravity waves are ripples of warped space that arise from changing gravitational fields. Anytime two objects of considerable mass are pulled into orbit, their acceleration and inward spiral catalyses gravity ripples, which stream off omnidirectionally as they disturb the space around them, analogous to the way in which sound waves disturb an atomic medium. But the only echoes of this kind we can really hear are the ones emanating from the most massive objects in the universe, neutron star and black hole mergers. By using a pair of extremely precise and sophisticated laser interferometers known as LIGO, even the most subtle gravitational disturbances can be seen wobbling the laser's light. Whether it's a pair of neutron stars, black holes, or a combination of the two, their pervasive influences would soon accelerate them to radical velocities of around half the speed of light in the second before they collide, rinsing the energy equivalent to several suns as they raise the space-time around them, producing a relatively low-frequency signal detectable across entire galaxies. By the time this wave signal arrives on Earth, it is nothing more than the whisper of a bygone cosmic cataclysm. But using LIGO, scientists can map the frequency of these signals as they intensify, creating a rising scale which sounds like a chirp when shifted into audible frequencies. Each of the mergers we've catalogued in the decades since our first has its own unique chirp as a signature, which can be used to reverse engineer the properties of the progenitor objects that came before. Like the majority of sounds we've covered so far, these chirps are a type of sonification. That is, an audible representation of some non-audio data, by turning signals into sounds which reflect them. For gravity waves, we are sonifying time domain oscillations, whereas the sounds of the solar system usually involve the sonification of radio data. And since the early part of the 2020s, NASA has been sonifying its visual data too, by taking its many stunning images of space and turning them into cosmic melodies, allowing us to listen to the universe in a brand new way. Beyond the solar system, our main source of electromagnetic data becomes the visual images snapped by NASA's space telescopes, like Hubble, Chandra, and James Webb. By mapping their pixels to musical parameters, like volume, pitch, and instruments, all kinds of celestial sights can be converted into anthems of space. And so, instead of a residual whir from a trailing wave of radio energy, this type of sonification involves representing images through sound to create complex cosmic harmonies. In truth, this type of sonification doesn't offer us the opportunity to advance our findings or uncover any new information, but it does nonetheless play another role, which proved wildly successful during the stay-at-home stints of the early 2020s. The ability to listen to the universe on any device and hear its many spatial features represented through sound has unlocked a new way for people to engage and connect with astronomy, especially for those who are blind and visually impaired. In fact, this was one of the main motivations behind the establishment of the System Sounds Initiative, a collaboration between Chandra telescope scientists and musical engineers at NASA to produce coherent melodies from real-world telescopic data. Over the past few years, they've produced dozens, if not hundreds, of sonifications from a variety of space's contrasting corners, capturing everything from the orbits of exoplanets to gusts of pulsar wind and even the hums of black holes hundreds of millions of light years beyond Earth. One of the earliest sonification projects, which was a key stepping stone in establishing the System Initiative, was the melody of the TRAPPIST-1 system, featuring 7 known exoplanets orbiting a small red dwarf star. One of the simpler pieces, the orbits of each exoplanet were mapped to a certain piano key, and gradually introduced to build up to a dramatic finale. Further afield, we find the downtown region of our Milky Way galaxy, the jam-packed galactic core where its supermassive black hole is hidden. The detail and complexity found in views of this area made for a much more ambitious target for a sonification, which required overlaying images in various wavelengths and assigning instruments to each class of luminous object. From side to side, the pieces then played to give us this sonification. Moreover, NASA took this project a step further by converting the sonification into sheet music to be performed by a live orchestra, in a piece called Where Parallel Lines Converge. Since then, orchestral pieces have been drawn up for the star R Aquarii, the Sombrero Galaxy, and even James Webb's infrared view of the galaxy grouping Stephan's Quintet. And then finally, perhaps the most famous cosmic harmony of them all, is the sonification of a monstrous supermassive black hole, namely the one lying at the heart of the Perseus cluster of galaxies, a 250 million light-years from Earth. In 2003, the Chandra telescope's X-ray eyes painted a picture of turmoil at the heart of this cluster, as its central black hole gobbled up swathes of gas from its surrounding environment, burping radiation back in the process, and in turn, churning out the lowest frequency acoustic sound waves ever discovered. In this dense, gaseous environment, the concentration of atoms is such that the faintest, softest sound waves are able to stream through the gassy interstellar medium. The black hole itself is emitting a vanishingly faint whirring sound as it feasts, B-flat in pitch, some 57 octaves below middle C. For comparison, the time period of a middle C oscillation is about 4 milliseconds, whereas the period of these waves was almost 10 million years. Therefore, scientists had to amplify the wave's frequency by hundreds of quadrillions of times to make it audible. But regardless, it provided the perfect natural basis for producing an authentic sonification, based on real sound data from hundreds of millions of light-years beyond Earth, revealing the ominous sounds of a supermassive black hole to the world. And it was this piece, in particular, which captured the ears of humanity, with the viral story reaching more than 2 billion people worldwide. But no matter how tuneful and impressive these melodies are, none of them represent the true sound of the universe. For that, there is only one real answer: the residual sound of the birth of space, which paints the oldest picture of the cosmos we currently have, the CMB. The cosmic microwave background is the cold, omnipresent radiation that once propagated as the Big Bang's last light. When the explosive inception of the universe ended, its final flash of photons was scattered and freed to roam clear space forevermore. These photons persist to this day as the oldest, coldest light signal in the universe, but not a signal of visible light, rather a microwave band radio static. When flicking between the airwaves of an analog television, you are met with a glitchy grey backdrop, often accompanied by a hissing sound. And while the vast majority of this is accounted for by stray, leaky earthbound transmissions, around 1% owes its existence to a much spookier source: the sound of the universe. The leftover radio noise from the Big Bang, which ironically took the form of light during the loudest explosion in history. Though we've covered a breadth of eerie, atmospheric cosmic anthems in this video today, it is the sound of the CMB that recalls our deepest memories of the cosmos. And with that, I bid you good night. C signing out.